The next thing we want to look at is the rules for negation. Rules for negation are not as easy to come by or as obvious as the rules for the previous connectives. Our question is, under what circumstances can we draw the conclusion that not phi? Well, we can draw the conclusion that not phi whenever it's shown that phi cannot be the case. That is to say, if we assume phi and then derive a contradiction, then we can write not phi. Now remember, contradictions are formulas that are never true, no matter what. So we need to introduce a new symbol to stand for a contradiction, and that's just what's on the screen right now. We have this little upside down T. Technically it's called falsum. And this symbol just stands for any formula that's always false. That is to say, any contradiction. Now we can write falsum anytime we have a contradictory sentence in the proof. And that can only occur if we have made certain contradictory assumptions. So when we have contradictory assumptions, we'll be able to introduce this falsum symbol, and deriving the falsum symbol can be considered the elimination rule for negation. So put more simply, if we assume phi and we can also get not phi, that is to say if we have some contradictory assumptions, we are then able to write falsum on a new line, and then we'll appeal to our elimination of negation rule. Here's an example of that. The idea here is that we have a set of contradictory assumptions. So suppose we have if P then not Q. Suppose we have Q and P. Well, we can see that taken together, these are contradictory assumptions. None of them by themselves is contradictory, but when you put all of these together, you end up with contradiction. So that's what we want to show here. How are we going to do that? How are we going to prove that this is contradictory? Well, look, we have P, which is the antecedent of this arrow statement. And we know that because of the elimination of arrow rule, if we have the antecedent of an arrow statement, we can then write the consequent. So now we've derived not Q using our elimination of the arrow. Well, now look at lines 2 and 4. We have Q and not Q, and that's exactly the ingredients we needed. So now we can write falsum on line 5 and appeal to our elimination of negation rules for lines 2 and 4. So when you're using the elimination of negation, which lines do you write here? You look for where is the contradiction, where is the statement of phi and not phi. Well, in this case, it's on lines 2 and 4 with Q and not Q. Now that's useful because it leads into our negation introduction rule. If we can derive falsum or a contradiction from some premise phi, then we can draw the conclusion that not phi. So if you have some assumption of phi and you show that that assumption leads to contradiction, then you know that phi cannot be the case because phi has contradictory consequences. That permits you to write not phi. So here's an example of that. Suppose we want to prove that P implies not P. So the idea here is a double negation is the same thing as the original statement. So suppose you say, I'm going to the store, and someone says, oh, you're not going to the store. That'd be an odd thing to say, but saying I'm not going to the store is the same thing as saying I am going to the store. It's not the case that I'm not going to the store is the very same thing as just saying I'm going to the store. Now again, in everyday life, there'd be no reason to say I'm not going to the store unless you're just messing with people. But in logic, it'll be a very important thing to understand that double negation is the same thing as the original statement. Now, Hegel, for example, is a philosopher who disagrees with that. He doesn't think that a double negation ends you back up where you started, but that's a whole other topic. Okay, so how are we going to proceed with this proof? Well, again, as with any proof, we start by listing our premises as assumptions. And what we want to do is show that we can derive a contradiction through some contradictory assumptions. So what are we going to do? We're going to assume not P. And we want to, well, what we want to do is arrive at not P. So we need to show that not P leads to contradiction so that we can put a negation in front of it. Because remember, how does our introduction for negation rule work? Well, it allows us to show that if phi leads to contradiction, then we can stick a negation in front of phi. What do we want to stick a negation in front of here? Well, we want to stick a negation in front of not phi. And so we need to assume that not P so that we can then stick a negation in front of it and get not P. And you can see that this is going to be a really easy proof because immediately once we introduce not P, we see that we have a contradiction. We have P and not P. Well, that allows us to write falsum according to our elimination of negation rule. And that's what we needed, right? We've got an assumption that leads to contradiction. Here we have not P leads to the contradiction. So we draw a box around our assumption. Remember, that just shows we were just assuming not P for the sake of deriving something from it. Now we're never going to appeal to that assumption again, so we draw our dotted box around it. And now we can stick a negation in front of the guilty assumption. The guilty assumption was not P, so we can stick a negation in front of not P. Now we have not P, and that's exactly what we were after. So we're done with our proof, and of course we appeal to the rule as always. This was the introduction of negation, and which lines was it operative on? Lines 2 and 3. Here's another example. Suppose we want to show that not P, so P with 3 negations in front of it, implies not P. This is sort of like the double negation thing. Whenever you have 2 negations, you know that those cancel each other out. That's essentially the point we mentioned earlier in the video. So we want to show that here we have 3 negations, so 2 of those cancel each other out, and it's just the same thing as having 1 negation. So having 3 negations, same thing as having 1 negation. That's, again, intuitive because double negations cancel each other out, but let's prove that formally. Now this is a good example to understand really well. We need to prove that not P, and the only way to do that is to go from P to falsum inside a box. Okay, so we know we want to assume P because ultimately what we want to get to is not P. Since all we have to work with is not P, we need to try to get not P. So we're going to need an embedded assumption here. We need a new assumption, not P. That's going to allow us to get not P. How? Well, we already see that we have a contradiction here. We have P and not P. So that leads to falsum. We can write falsum on this line and appeal to our elimination of negation rule on lines 2 and 3. We draw our box around it, and we conclude using introduction of negation that not P must be the case. Remember, that's because we assumed not P. We showed that derived a contradiction, and now we can stick a negation in front of the assumption. So that's what we've done on line 5 here. Notice, now that we have not P, That's a direct contradiction with line 1. So now we can have another line with falsum on it. That's the elimination of negation rule on lines 1 and 5, because here we have a direct contradiction. We have a formula, and then we have that formula negated. Well, we've shown then that P ultimately leads to a contradiction. So that allows us to stick a negation in front of this assumption, and that's precisely what we wanted to show.